Today we will understand the concept of hermeticity of operators in function space. Hermeticity or Hermitian operators in function space. Okay. So let's recall what we learned about Hermitian operators in the case of finite dimensional linear vector spaces. In those cases, it's actually quite easy to understand. In finite dimensions, right? An operator A can be written as a matrix. Okay. And if the matrix A is Hermitian, the words if matrix A dagger equals A, we say that the corresponding operator is Hermitian. Okay. Now the proper definition of Hermitian operator is as follows. Suppose if we have two vectors, f and g, or a and alpha and beta, or whatever it is, let's call alpha and beta. Then suppose if you construct the inner product of alpha with a beta, okay, this should be understood as the operator A acting on beta to give you the new ket A beta. And now we are constructing the inner product of alpha with the ket A beta. Right? And suppose if you have another operator, suppose you have another operator B such that the inner product of alpha with A beta is the same as the inner product of B alpha with beta, then B is the adjoint of A. This was our definition, okay? So the symbol for adjoint of A, as you know, is A dagger. So we say B is equal to A dagger. But it should satisfy the crucial property that the inner product of alpha with A beta is the same as the inner product of B alpha with beta, right? Okay. Now there is, before I proceed, I would like to tell you that there is a slight technical aspect to this discussion of Hermitian versus self-adjoint. Okay. Now, if the operator A is Hermitian or self-adjoint, we are using the term interchangeably, Hermitian and self-adjoint loosely. So what we have basically said that if the operator A dagger is the same as A itself, A equals A dagger, then we say the operator is Hermitian. Okay. And in this lecture, I would also use the word self-adjoint. Oops. Self-adjoint. Okay, interchangeable. But strictly speaking, this is not correct. And Hermitian and self-adjoint are two different properties, okay, of operators. Particularly in function spaces, this becomes very important. In finite dimensional Hilbert spaces, of course, the distinction between them is not very important. But in function spaces, the distinction between them is technically important, even though I will gloss over this fact in this particular course. But I'm sure you would learn more about this in your mathematical physics course. Self-adjoint is slightly more tricky and technical, and it also has to do with how you define the domains and ranges of operators, the number of functions that are actually allowed to be acted upon with this operator, and the domain and range for the operator and its adjoint should match exactly for an operator to be called self-adjoint. So we will not get into such specifications in this course. We will use the words Hermitian and self-adjoint interchangeably, but please understand for educational purposes that in infinite dimensional spaces, these are strictly not the same things. Okay. So with this caveat, let's go ahead and understand how should we construct the Hermitian adjoint of operators. Okay. So let us take as an exercise the problem, construct the Hermitian adjoint, or not adjoint operator, adjoint of the operator ddx in L2. Okay. Now I will leave, I'll do it in L2 with some length a and b. And then we will make a to be minus infinity and b to be plus infinity. But for now, I will keep this length to be some ab. So this is L2 is simply the Hilbert space where the norm is defined to be square root of x1 square plus x2 square plus blah, blah, blah. And a and b are the limits. Okay. So again, what is my definition of adjoint of the operator? Suppose if I have two functions, f and g, then the adjoint of ddx should be constructed according to the prescription alpha. Let me not say alpha and beta, let me call f and g. F ddx acting on another vector g. Okay, this should be the same as some operator, let's call this operator O, acting on f g. Okay. Now, naively, one might be tempted to think that the adjoint of ddx is the same as ddx, but you would actually quickly see that this is not true. Okay, let's actually do the calculation. So let's compute the left-hand side of this. Our job is to understand what O is. Okay, or if there is a O such that this equation is valid. All right. So remember the definition of inner product in function space. This is equal to a b f star of x g of x dx. This is the definition of inner product that we are going to be using. Okay. So with this definition, what is f dg dx? This is equal to integral a to b f star of x, the function dg of x dx times dx. Okay. Now, if ddx is the Hermitian adjoint of itself, then let us assume that the O that I've written in this top equation is ddx itself. Then if I have this inner product, right, if ddx were self-adjoint, then this should be equal to a to b df star dx times g of x dx, right? So if ddx were a self-adjoint operator, then equation 1 and equation 2 would be the same, right? So let us check if they are the same. So let's take equation 1 and evaluate this using the famous UDV formula. So integral a to b f star of x dg dx dx, right? So this is my u and this is my dv, right? So if I do that, this is equal to uv. So the first term is a boundary term, f star of x, g of x, between b and a, minus b du, ab, g of x, du is df dx times dx. Okay. Now, if you stare at equation 3, there is no sense in which equation 3 looks like equation 1. There is, if you want equation 1 and equation 3 to be exactly the same, then you have to get rid of the first term, right, which is called a boundary term. So you have a boundary term. Excuse me. Okay, that is the first offending piece. Now, even if I were to get rid of this boundary term somehow, I still have a negative sign to contend with. So if you forget this boundary term, then equation 3 gives me minus integral a to b g df dx df star dx dx. But equation 2 is plus integral a to b df star dx g of x dx. So there is a negative sign that is still bothering me. So there is no sense in which I can say that equation 2 and equation 3 are the same things, but I can try to get close to trying to define the Hermitian adjoint of ddx operator. the way I will get close is by saying that you have to choose functions such that they either f of x equals 0 at x equals a comma b. That is certainly possible. If f of x is 0 at either a or b, or equivalently, f star of x, but if f of x is 0 at a, b, f star of x is also trivially 0 at a, b. Or if this combination f star g at b is the same f times g at a, at x equals a, is the same as f times g at x is equal to b somehow. Right? And that seems a little more artificial. The first equation is a lot more practical. So whatever it is, if I want to get rid of the boundary term, so this is a very natural choice that I can employ. For example, this is just one possibility. There is also other possibilities, but whatever it is, you have to admit for the fact that if you want to define the adjoint of ddx, you have to be in a space in which you cannot choose all kinds of functions randomly, even though they might be normalizable, but you have to choose functions such that they get rid of the boundary term. Now, if a were to be minus infinity and b were to be plus infinity, then this is trivially satisfied, because as long as I choose functions that are normalizable, whose length does not blow up, then these functions f at plus infinity equals f at minus infinity, this is always equal to 0 for normalizable. Okay, and mostly quantum mechanics is formulated in the space L2 minus infinity and infinity. And in this space, I can always get rid of the boundary term, because for any reasonable function, its values at x is equal to plus minus infinity is always equal to 0. So I can get rid of the boundary term. So in the space L2 minus infinity plus infinity, I have the curious looking formula that the adjoint operator of ddx is not actually ddx, but the adjoint of ddx, which I will symbolically denote as ddx dagger, is actually equal to minus ddx from equation 3. If I get rid of the boundary term, then equation 2 and equation 3 are not the same, but I can still conclude that if I put the negative sign onto the ddx term, I can conclude that if for the operator minus ddx, it satisfies the equation that integral a to b f star dg dx is the same as integral a to b g minus ddx f star dx. Okay, so in the space where in the space L2 minus infinity plus infinity, or in the space L2 AB, where the functions have been properly chosen such that the boundary term is 0, we can conclude that the adjoint operator of ddx is actually equal to minus ddx. Okay. So which means that ddx is not a very good operator in quantum mechanics, because it is not self-adjoint. Not self-adjoint, or equivalently, or not Hermitian. But remember, postulate 2 in quantum mechanics tells you that all operators of corresponding to observables in quantum mechanics are actually Hermitian operators. So ddx itself cannot correspond to any physical observable. But as you can easily check, the operator iddx is self-adjoint. Okay, I want you to check this. It's actually trivial to check. If you go through the same computation, you'd actually find that if you take the adjoint of the operator, since ddx is manifestly real, the adjoint becomes ddx. But if you take iddx, if you want to switch the order of operation in your inner product, you'd actually pick up a negative sign from the I also. That negative sign from the I will kill the offending I over here, and you will get an operator that is manifestly self-adjoint. Okay, so the operator IDDX is actually self-adjoint. So this operator IDDX is of fundamental importance in quantum mechanics, as you well know, because this is the representation of the momentum operator with an H bar, of course, in the X space. Okay. So you have to be careful when checking for hermeticity of operators in infinite dimensional Hilbert spaces, because you have to actually do the calculation and then figure out if an operator is self-adjoint or not. It is not straightforward as in the case of finite dimensional vector spaces, because in those cases you can just look at the matrix corresponding to the operator and see if the dagger of the matrix is the same as the matrix itself. But the process of checking for self-adjointness or hermeticity in infinite dimensional Hilbert spaces is slightly trickier. So I will give you a homework, which will also be part of your tutorial. Homework: check if the operator d square dx square is Hermitian in L2 minus infinity, infinity. Okay. In this case, you have to do two partial integrations to transfer the d square over. So what you have to do is try to check if f d square g over dx square, oops, is it equal to d square f over dx square g. Okay, to check this, you have to do two partial integrations. You take the left hand side or right hand side, one of them, and do two partial integration to transfer both the derivatives from g onto f, and then check if this equality is satisfied. Okay? And you would actually find that it is satisfied. So even though the operator ddx is not Hermitian, you would actually find that the operator d square dx square is actually Hermitian in quantum mechanics. And the operator d square dx square is also of fundamental importance in quantum mechanics, because as you can easily guess, the kinetic energy operator T, which is equal to p square over 2m, is actually equal to minus h bar square over 2m d square over dx square in the position representation, the X space. Okay. So since this is Hermitian and any function of X is trivially Hermitian, I can write any function of X operator. X operator is Hermitian in, as you can easily check for yourself, because there is no associated problems with it. I can add any T operator with any function of F. Okay, I will call this function of X some V of X. This operator is actually Hermitian, and this operator has a name. This is called the Hamiltonian operator. If the potential, if V is associated with the potential image. Okay. So how would you actually construct this? So suppose if you have a classical potential, for example, a simple harmonic oscillator, right? So the classical potential of the simple harmonic oscillator is 1/2 m omega square x square. The corresponding quantum mechanical operator is, you replace the x that appears here with the x operator. Okay, which means the Hamiltonian for a simple harmonic oscillator in quantum mechanics would be given by p square over 2m plus 1/2 m omega square x. Okay, that is how we construct operators in quantum mechanics. And since the Hamiltonian is a Hermitian quantity, it is actually a measurable quantity in quantum mechanics. And the measurement of Hamiltonian of a system gives you the energy of the system. Okay, all right. This stuff you know. So this is the first thing that I wanted to talk about in today's short lecture. You have to learn how to check for the hermeticity of operators in function space. Okay. The second is more related to the X and P operators. You have to understand if they commute or don't commute. Okay. So you have to learn about the commutation of operators in function space. Now, in the case of finite dimensions, this is again very easy. You just take the corresponding matrices, right? Suppose if you have two operators A and B, in finite dimensions, you look at, excuse me, you look at the matrix formulation of A and B and simply calculate AB is equal to the product of the two matrices AB minus the product of the two matrices BA. Okay? Now the definition is also the same in function space, except that I don't have matrices because these are all infinite dimensional spaces. So I need to understand how to calculate this commutator. So the first and the most important commutator that we have to calculate is a commutator of X and P. Okay. Now the way you calculate commutators is, again, as I told you, an operator by itself is meaningless. So you have to add the operator on some function and then you can get a meaningful result. So let me choose a test function f of x and add this combination of operators on the test function. Okay. And then I will do this in the x space, coordinate space, the x representation. In the x representation, in the x basis, the operator x simply multiplies the corresponding function by x, and the operator p simply takes the derivative of the function upon which it is acting. Right? So x comma IH bar ddx acting on f of x would be equal to, the operators x times the operator IH bar ddx acting on f of x minus the operators taken in the reverse order. So IH bar ddx acting on x acting on f of x. Okay. Remember that the order is very important. In the first term, the ddx acts only on the test function f of x. In the second term, the ddx acts both on x and f of x. The way you understand this is the x operator acting on f of x would give you the corresponding value of x times f of x. And now the ddx will hit on both the x and the f of x. So let us do this calculation. The first term is basically IH bar x df dx. The second term is minus IH bar ddx acting on x times f of x gives me two terms. The first term is x df dx. The second term is f times ddx acting on x is just 1. Okay. Now you find that this term and this term would cancel and you would get this is equal to minus IH bar F1. Okay. So this short calculation has revealed to me that I have made a sign error, right? So the sign error, sorry, I'll stop sharing, share again. So the sign error that I've made is I chose the operator to be IH bar ddx, but I should actually choose minus IH bar ddx. Okay. So if you put a minus sign consistently everywhere, minus, this would actually be a plus. Okay. So the momentum operator, I chose with the wrong sign. The momentum operator should be minus IH bar ddx. So how, all said and done, what is this commutator? This commutator is basically now, oops, excuse me, use the right color. X comma minus IH bar ddx acting on the test function f of x equals IH bar times the test function f of x, which means this combination of operators acting on a test function simply gives me IH bar times the test function. Now the job of the test function is done. I can take out the test function. So now the commutator is simply, I can write this commutator as an operator function, operator equation as x comma p equals IH bar times the unit operator. Okay. So this is the famous XP commutation relation. And since X and P do not commute, we have the famous uncertainty relation between the two. Remember from our earlier discussions, we know that if A and B do not commute, then the variance of A times the variance of B has a fundamental uncertainty, and this is greater than or equal to 1 over 2i times the expectation value of the commutator of A and B, the whole thing squared, right? So let us apply this to x comma p. Sigma p squared times sigma, x squared is greater than or equal to 1 over 2i times the expectation value of A and x and p, which is basically, so I'll write this is sigma x, sigma p, even though it doesn't matter. IH bar times the unit operator, the whole square. Okay. Now the expectation value of unit operator is just 1, because in any basis expectation value of an operator is given by psi over psi. The expectation value of the unit operator is psi. 1 acting on psi is just psi, and for any properly normalized state vectors, this is equal to just 1. Excuse me. So I can write the product of the variances sigma x square, sigma p square has to be greater than or equal to 1 over 2i times IH bar quantity square, and this is equal to h bar square over 4. You notice that the I cancels out as it should, okay? Because the left hand side is an error in measurement, so it cannot have any complex quantity. Taking this positive square root, we find that the product of the uncertainties in the measurement of position and momentum has to be greater than or equal to h bar over 2. Okay? So this is Heisenberg's famous uncertainty relation as applied to the x and p operators. I will put this in a box. I'm sure many of you have seen this before. So the physics of this equation is that if I make a measurement of the position and the momentum of an object, then the uncertainty in the position measurement times the uncertainty in the momentum measurement is always greater than some fundamental quantity, which is equal to h bar over 2. Which means I cannot, if I make the uncertainty in the position as low as possible, then the corresponding uncertainty in momentum has to be as high as possible, so that the product is equal to a finite quantity, which is equal to h bar over 2, at least h bar over 2. Conversely, if I make the momentum measurement as fine as possible, then I lose track of where the particle is, because the uncertainty in the corresponding position measurement is too high, because the product has to have at least a minimum value equal to h bar over 2. This is Heisenberg's uncertainty relation as applied to the x and p operators, but note that this applies to any two operators that do not commute. As long as the operators don't commute, if you look at this equation, as long as the operators don't commute, the right hand side is non-zero. Okay, if two operators do commute, then of course I can measure them accurately simultaneously, no problem. Okay, so that is basically what I wanted to cover in this short lecture. The next lecture we will take up Schrodinger equation back again, and then discuss some of the general solution of Schrodinger's equation, and then we will start talking about certain specific problems.